in the preceding couple videos, we've talked about two different kinds of snow grains that are formed by metamorphism. First, we talked about facets, then we hit on rounds. Now, I want to talk about the final kind of snow grain that can be produced by metamorphism, which is melt-freeze grains. Like facets and rounds, melt-freeze grains have some specific characteristics that will help you identify them when you encounter them in the snowpack. So first, melt-freeze grains are relatively large, and as they develop, they will get noticeably larger. Second, melt-freeze grains are very spherical in nature. If you pick one up, it almost looks like a little marble. And third, melt-freeze grains have this icy appearance. And all of these attributes are a product of how melt-freeze grains are formed. True to their name, melt-freeze grains are formed by consecutive melt and freeze cycles, or freeze-thaw cycles. So without further ado, I'm going to dive into the processes that drive the formation of these grains. So we're going to start by zooming way in and visualizing some snow grains. And as you can see, these snow grains exist in all different sizes within the snowpack. In order for water to melt, which is the first process that leads to the formation of melt-freeze grains, it needs to be exposed to temperatures at or above 32 degrees Fahrenheit or freezing. So let's go ahead and say that the ambient air temperature is greater than 32 degrees Fahrenheit. And this is a surface layer of snow, so it's starting to experience those warm temperatures. And as a result, the smallest grains of snow are beginning to melt. As these droplets of liquid water move through the snowpack, they're going to begin to collect on the surface of larger grains of snow. And if the temperature drops below freezing, these droplets will actually freeze into an icy lens that surrounds the grain of snow. Now, a single cycle of thawing and freezing usually isn't sufficient to transform a snow grain into a melt-freeze grain. So let's go ahead and imagine that once again, the air temperature rises above freezing. And once again, those smallest grains of snow melt into liquid water. As we described before, the droplets of liquid water will begin to collect on the surface of the largest grains of snow as they move through the snowpack. And if the air temperature once again drops below freezing, they will freeze into an icy lens. So essentially what's happening is that the large grains of snow are cannibalizing the smaller grains of snow. Through multiple rounds of freezing and thawing, the small grains disappear and are incorporated into the larger grains. And this process, metamorphism driven by freeze-thaw cycles, is called melt-freeze metamorphism. And this process is also what gives melt-freeze grains their specific characteristics. As we saw, their size is a product of the melting and freezing that's occurring on their surface. They're also very spherical due to this, and that icy appearance is due to the fact that they are comprised mostly of ice. It's worth noting that because these grains require repeated melting and freezing to form, they generally tend to form, especially in Alaska, in the springtime. And you'll often hear people referring to melt-freeze grains as corn snow. So I'm sure at this point you guys are like, great, cannibalistic snow grains. But what does this have to do with avalanches? Specifically, do melt-freeze grains increase or decrease the stability of the snowpack? And the answer is that they do both. They're capable of increasing and decreasing stability. But what drives this is how much liquid water is present in the snowpack with the melt-freeze grains. So let's go ahead and dig into this a little bit and imagine a snowpack made up entirely of melt-freeze grains. During a warm spring day, these grains are going to be well into the melt portion of melt-freeze metamorphism, which means that they're sharing the snowpack with a lot of liquid water. And what this liquid water does is it lubricates these grains. So it decreases the amount of cohesion they have. I think it's helpful to imagine a bucket full of marbles and water, because that's essentially what these snow grains are in the snowpack. So in this case, the liquid water is undermining the stability of the snowpack. Now imagine that the sun goes down and the temperature drops. Now these melt-freeze grains are going to enter the freeze portion of melt-freeze metamorphism, which means that the liquid water within the snowpack is going to freeze into its solid form. Now, while some of the liquid water will freeze on the exterior of the grains and contribute to the further growth of the melt-freeze grains, some will actually freeze between the individual grains, forming ice bridges. And the formation of these ice bridges increases the cohesion of the snowpack, which in turn increases the stability of the snowpack. So as the amount of free liquid water in the snowpack decreases, the stability goes up. So we've talked about some of the specifics of melt-freeze grains. We've talked about how they're formed, how this formation contributes to their specific characteristics. We've also talked about how they can contribute to stability and how they can undermine stability. But now I want to talk about freeze-thaw cycles or melt-freeze cycles and how these cycles, which are contributing to the formation of melt-freeze grains, can impact the snowpack as a whole. So let's go ahead and imagine, shocker, Earth at the bottom of the snowpack. And on top of it, let's throw a nice thick layer of snow grains. Now, in order for a melt-freeze cycle to occur, you need to have the melt, and any number of atmospheric conditions can contribute to melting. The first and most obvious is an ambient air temperature greater than 32 degrees Fahrenheit. Alternatively, if the sun is intense enough, it can actually warm the snowpack to above freezing. And a third option is pretty obvious as well, which is rain. Rain is pretty good at melting snow. So for this example, let's imagine a sunny day in late March that is above freezing. Now, the combination of the sun and the warm temps are going to begin to melt the small snow grains that are in the upper layers of the snowpack. And as a result, there's going to be an increase in the amount of liquid water present at the top of the snowpack. When the sun sets, it's going to drop the air temperature, and all that liquid water in the snowpack is going to freeze. So it's going to both contribute to the formation of melt-freeze grains, as we described earlier in this video, as well as forming ice bridges connecting the different snow grains. When the sun comes up and the air temperature rises, this process is going to repeat itself. So the smallest grains of snow will again melt, and the ice bridges connecting the melt-freeze grains will also melt. And as a result, you're going to see more liquid water in the snowpack. Now, this liquid water is going to eventually percolate down deeper into the snowpack, which is going to contribute to more melting. So you'll see more liquid water dispersed deeper into the snowpack, which means that when the sun goes down and the temperature drops again, more of the snowpack is going to freeze. I think it's worth noting that the term used to describe this layer of frozen snow, which is made up of melt-freeze grains and ice bridges connecting them, is called a melt-freeze crest. Now, this process can continue indefinitely. The sun can come up, the air temperature can rise, the upper layer of the snowpack can begin to melt, increasing the amount of liquid water present, which then percolates down through the snowpack, contributing to melting in deeper and deeper layers of the snowpack. And then once again, the sun can go down, and all of that liquid water can freeze into a robust melt-freeze crust. And in case you haven't gotten the point yet, the sun can come up once again. thawing those upper layers, which causes an increase in the amount of liquid water, which then percolates down through the snowpack, melting deeper and deeper layers until the entire snowpack is saturated, which, when the sun sets, will freeze in its entirety. And I think at this point, you're probably noticing what I'm trying to drive home, which is that subsequent freeze-thaw or melt-freeze cycles will cause a thicker and thicker crust to form. All right, so to wrap up this video, I just want to briefly summarize some of the things we've covered concerning melt-freeze grains. So first, true to their name, melt-freeze grains are formed from repeated cycles of melting and freezing. And the result of repeated cycles of melting and freezing is a process called melt-freeze metamorphism, which is, in essence, just larger grains of snow cannibalizing smaller grains of snow. Because these grains require melting and freezing, in Alaska, they tend to occur in springtime snowpacks. And the last little nugget I want you to take away with you is that you can determine the stability of a snowpack that consists of primarily melt-freeze grains by looking at how much liquid water is present. Because liquid water is going to destabilize the snowpack, while the presence of frozen water in the form of ice bridges is going to increase the stability of the snowpack. All right, thanks guys. I'll catch you in the next video.